Hello, this is Sadbir. In this video tutorial, we will discuss the three main consequences of axiom of completeness. They are nested interval property, Archimedean property of real number, and also the dynasty of rational number. So let's begin with the recall of what is the axiom of completeness. We have discussed the axiom of completeness in the last two videos, so please watch them before if you are on this video. So axiom of the completeness is an assumption which is basically made on every subset of real number which is non-empty and bounded above. So for example, if you have a which is a subset of real number, and if this set is non-empty, and also this is a bounded above, then we assume that A has a least upper bound, or in other word, the sup of the supremum is also known as the least upper bound. The sup of A exists, and that sup is a real number, so it belongs to the real number. So the supremum of any non-empty bounded above set exists, and it is a real number. You can also basically make another assumption. If the set is bounded below, in this situation, instead of having the least upper bound, that will guarantee this axiom that it has a greatest lower bound, or in other word, the inf of A exists and it is a real number, exist and belong to a real number. So basically, this is the another axiom, which is we basically assume if the set is bounded below. So every result which is almost true for the bounded above set, that result is also true for the bounded below set in this course. Now let me give you the first consequences of the axiom of completeness, which is also known as nested interval property. So here is the statement of the nested interval property. The statement say that if we have the sequence of a closed interval which are nested, or in other word, I1 is contained in I2, I2 contains I3, and so on, then the intersection of these all interval is non-empty, or in other word, there exists at least one real number which belongs to the each interval A and Bn. And also notice all these interval, they are closed. If the interval are not closed, this statement is not true. Now let me draw the picture of this statement so that we can basically have more clarity what this statement is asking for us to prove. The first we will draw the real line, and then we will plot all the intervals on this real lines. So as you can see, the interval A1, B1, that is our first closed interval. Then the interval A to B2 is nested in, or it is completely contained in the interval A1, B1. And the interval A3, B3 is again, it is contained in the interval A2, B2, and so on. So this process is keep on going on. Then AN is contained in, it is a previous BN, and so on. So this process is basically go forever. So as you can see, the intersection of this these interval will be it will contain basically the entirely ANs for all N's. And we will prove that this intersection is, no matter how many intervals we take, this intersection will contain at least one real number, x0 will belong to the real, so that x0 will belong to the intersection and vary from 1 to infinity in. So this is the basically the explanation of this statement is that if we have the interval which are nested like that, even though these are infinite many interval and their intersection still will be non-empty, or in other word, there will exist a real number which will belong to this infinite intersection. To prove this theorem, so basically what we need to do is we need to find that x0. We need to prove that there exists some x0 which will belong to this intersection. So to begin the proof, I will construct this proof. So this proof will be some sort of by construction. So first I will construct the set A. In that set A, I'm going to take all the left end point of these intervals. And but there is a one property that is this set has that all ANs, they are always less than or is equal to B1 for all n belongs to set of natural number. As you can see from the picture also, all the ANs, they are always less than or is equal to B1, B2, B3, and so on BNs. So this is the definition of the bounded above set. So this implies that A is bounded above and it is also clearly non-empty. So since this is a bounded above and non-empty by the axiom of completeness, we can find x0, which is a real number, and that x0 is the sup of that set A. Since x0 is the sup of A, so this implies x0 is greater than or equal to every element of that set, or in other words, every greater than or is equal to every an for all n belongs to set of natural numbers. And also we know because every bn's, they are always greater than or is equal to every element of the set A. So therefore, all the bn's, they are the upper bound for A, and it is also clear from the picture that each bn is greater than or is equal to each an. So therefore, if this is a upper bounds and x0 is the least upper bound, so x0 must be less than or is equal to each bn's for all n belongs to set of natural number. Now we can combine this inequality and this inequality, and this will give us, so this will implies an is always less than is equal to x0 and x0 is always less than is equal to bn for all n belong to set of natural number. And this is what we need to prove, that x0 is always in the interval a and bn. So it implies x0 is always in this closed interval a and bn for every values of n, or in other word, x0 is in the intersection of the set ins. N vary from 1 to infinity, or in other word, the set of all natural number. So this proves our theorem that there exists at least one real number which is in the intersection. Therefore, this intersection is non-empty, so that because we found that there was a one element in that intersection. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, I will show you the second consequences of the axiom of completeness, which is the Archimedean property. The statement of the Archimedean property has two parts. In part 1, we will show that any real number x, we can always find a natural number which is strictly greater than this real number x. In the second part of this statement, we also show that if we have a positive real number, which is a strictly positive, then we can always find a natural number n, so that the reciprocal of that natural number is strictly less than the real number y. Let me first show you the proof of the statement number 1. I will use the method of contradiction to prove the statement number 1. So I will assume that what if the statement number 1 is not true. So assume 1 is not true. If 1 is not true, it means the negation of that statement is true. So now let's find out first what is the negation of 1. So the negation of 1 is basically there exists a real number x which is belongs to R for all n belongs to the set of natural number, and they are satisfying this property. They satisfying n less than is equal to that real number x. So this is the negation of our statement number 1. So as you can see that for any or for all will turn into there exist, and there exist will turn onto for all, and the satisfying this opposite inequality when n is less than or is equal to x. Actually, this negation statement is simply saying that this set of natural number is bounded above. Because as you can see, what is the definition of a bounded above set? The definition of the bounded above set is it is all element of the set is less than or is equal to a real number x. So as you can see here, this statement is saying that there exists a real number so that all the member of the set of natural number are less than that real number x. Or in other words, it is saying that the set of natural number is bounded above set. So now if this is a bounded above set, and we also know this is a non-empty set, so we can use the axiom of completeness now. So by axiom of completeness, we know that this set must have a least upper bound. This implies the sup of this set, which is the set of natural number, will exist, and I'm going to call that sup is equal to alpha. So this will implies if this is the sup, then alpha minus 1 cannot be upper bound, not be an upper bound, because otherwise this will contradict the definition of the sup. If this is not an upper bound, so implies again we will use the definition of the upper bound. There will exist n0 which will be a member of the set. This time this set is the set of natural number, so that this member will be greater than alpha minus 1, because alpha minus 1 is not an upper bound. If I simplify this one a little bit, this means alpha is strictly less than n0 plus 1. And we know that since n0 is a natural number, so if I add one more in it, it will be a still natural number. So what we have basically alpha is strictly less than n0 plus 1, where n0 plus 1 is belong to the set of natural number, or in other words, it is the member of this set. And we assume that alpha is also the sup. If alpha is the sup of this set, which is the set of natural number, then alpha must not be less than any member of that set. But we are saying that alpha is less than one member of this set, which is the set of natural number. So this is the contradiction to the definition. So this is contradiction, is a contradiction to the fact that the sup of the set is alpha. If this is a contradiction, it means one is this statement is not true, or in other words, the statement number 1 is true. So this completes the proof of the statement number 1. Next, we will prove the statement number 2. The proof of the statement number 2 is really depend on the statement number 1. So what we have given a real number which is strictly positive and is also a real number. And since this number is strictly positive, we can compute the reciprocal of that number, and that number will be again a real number. So this number exists and it will be again a real number because this y is a strictly positive real number. Now I will use the part 1 of the statement. So 1 implies if this is a real number, so corresponding to this real number, there will always exist a natural number n, which is belong to the set of a natural number, so that this property, which is a n will be strictly greater than this real number, which is in this case is 1 over y. Now I will take the reciprocal of this inequality, or the reciprocal of these two numbers. If I take the reciprocal of n, it will become 1 over n, and the inequality will flip. And if I take the reciprocal of 1 over y, this will become y. And this proves our statement, set number 2. That is, for any real number, there exists a natural number whose reciprocal is strictly less than this real number y. Next, I have a quiz problem number 2 for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Last but not the least, our third main consequences of the axiom of completeness is the dynasty of rational numbers in real. Here is the statement of says that for any two real number, we can always find a rational number which is in between these two real number a and b. Or in other words, if you pick any two real number on the real line a and b, you can always find a number r which is a rational, or in other words, which is a p over q form. So there always exists a number which can be written in a p or q form between any two real number. Let's begin the proof of this statement. Since we have given a and b, they are basically two real number. And also it satisfies this condition, a is strictly less than b. So this will implies that b minus a will be strictly positive, and it also will be is a real number, because the difference of two real number is a real number. So therefore b minus a, which will be strictly positive, and it will be a real number. So if this is a real number, I can use by the second property of the Archimedean property. So by part 2 of what is the second part of the Archimedean property? If you have any real number y, which is strictly positive, you can always find a natural number which satisfy this property, that the reciprocal of that natural number 1 over n is strictly less than y. So that was the Archimedean property, the second part of this statement which we will use. So since b minus a is a real number, so I will use that b minus a is in place of y. So it means for b minus a, this is a real number, and strictly positive real number. There exists, corresponding to that real number, there will exist a natural number so that the reciprocal of that natural number will be strictly less than b minus a. So I simply basically use the Archimedean property, assuming b minus a is my y. So this implies if I multiply n on both sides, this will be a 1 less than is equal to nb minus na. And now I will move the na on the other side, or in other words, I will add na on both sides, and it will give me nb on this side, and so I will get this inequality. So this is important inequality, so I will box this one. Now let's make an observation. So as we can see, if we have a real line and na is now a real number, because n is a natural number and a is a real number. If I multiply n and a, it will be a real number. And you know that we can always find a two consecutive natural number, which will squeeze this real number na. So always we can find the two natural number or consecutive natural number, which basically the real number will basically be in between these two consecutive natural number. And now if these are the m and m minus 1 and m, they are consecutive real number, then if I add 1 in this real number, and I will get na plus 1 will be on the other side of m. So from this picture, I can conclude na is strictly less than m, and m is strictly less than na plus 1, and 1 plus na is strictly less than nb by using this inequality. Or in other word, if I basically write now na is strictly less than m, and this is strictly less than nb. I just ignore this piece, because if m is less than this and this is less than that, it means m is also less than nb. And therefore, this implies a is strictly less than m over n, and that is less than b. So this proves our theorem, because we found a rational number. So as you can see, this is a rational number. So this proof was a proof by construction. So we found a rational number m over m, which is in between the real number a and b. And that is what the statement is saying, that if you have the two real number, you can always find a rational number which lies in between these two real number. So this completes the proof of this theorem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.